said this once, but this is a piece of material that I think that math students ought to see at some point. There's and it's not really clear to me where they see it, and it's at least somewhat related to calculus. So this is as good a place as any. I mean, there is a section for this in the textbook. We don't normally have time to talk about it. And what just happened? The topic I have in mind is the hyperbolic trig functions. So when we define the sine and the cosine, probably we first see them in terms of right triangles, but eventually we define them in terms of the unit circle. You know, we have an angle, and this defines a point on the unit circle, and the x coordinate gives us the cosine, and the y coordinate gives us the sine. And the unit circle is pretty arbitrary. I mean, in fact, we have to define radians. We have to define an entirely new way of measuring angles for the unit circle to work particularly well. I mean, you could use this same concept to define a basically infinite class of functions. You know, if instead of a unit circle you had an ellipse, you could still define functions in the same way, the elliptical cosine and the elliptical sine. That's not standard. That's not something people do. But what people do is take this definition and replicate it with hyperbolas. And you know, circles are a conic section, and hyperbolas are a conic section. So we're not just selecting stuff at random here. There's a reason hyperbolas get selected. And there are going to be a few quirks in this definition. But we'll talk about the definition, and then we'll talk about what these are used for. We'll talk about exponentials. We'll talk about complex numbers. We'll get sort of a smorgasbord of material from out of this. So in particular, the unit circle is x squared plus y squared equals 1. So if we want to use a hyperbola instead, it probably makes the most sense to use x squared minus y squared equals 1. And this hyperbola, well, it has a piece over here, but only the piece over on the right is relevant. There are slant asymptotes. And the hyperbola looks something like that. And just like with the unit circle and the sine and the cosine, we draw lines and we look at where the line segment hits the curve, and we give those names. We call them the hyperbolic cosine and the hyperbolic sine. And these are abbreviated COSH. And you know, I've never quite known how to pronounce that for probably straightforward reasons: cosine, hyperbolic, sine, hyperbolic. And here it's going to seem like we're doing something that's different from what we do with the sine and the cosine, because if you're looking at this picture, this is probably what you're imagining. That's an angle x, and we use that angle to define the hyperbolic sine and the hyperbolic cosine. But it's not an angle that we're looking at. Instead, we're looking at an area. And the area of this region is not x. It's x divided by 2. So we're using areas instead of angles to define the hyperbolic sine and the hyperbolic cosine, and we're not using the area you might expect. We're making to find the cosh of x and the sinh of x. We create a region whose area is not x, whose area is x over 2. And what I am going to say is that actually this is identical to this, in the sense that this angle theta also generates an area, and that area is half of the angle. So we absolutely could define the sine and the cosine in terms of area if we wanted to. But why? I mean, granting that we can do this, what's the point? Well, the point is that this hyperbola has these asymptotes, and the hyperbola is stuck between these asymptotes. So if we were using an angle, that pi over 2 would be the maximum angle we could have. And we could not therefore define the hyperbolic sine and the hyperbolic cosine of pi or 2 pi or anything like that. On the other hand, using the area, we can make this area as big as we want by making the line, by making this line up here closer and closer to the slant asymptote. If we want to make the area bigger, we just go closer to the slant asymptote And by getting closer and closer to the slant asymptote, we can make our area as large as we want. So the point of this is that the hyperbolic sine and the hyperbolic cosine are defined for all real numbers. To make this explicit, just like we'd think of that as a negative angle. If we go down here, we'll think of this as a negative area. So that shouldn't be surprising to those of us who have now taken calculus. You get negative areas using the integral as well. And the hyperbolic sine and the hyperbolic cosine are, I feel like you have to see this definition, because if you don't see this definition, you're going to spend the rest of the period wondering where this word hyperbolic comes from, and also where these words sine and cosine come from. But the hyperbolic sine and the hyperbolic cosine can be defined very neatly in terms of the exponential function without any reference to hyperbolas. Hyperbolic sine is e to the x minus e to the negative x, all divided by 2. The hyperbolic cosine is e to the x plus e to the negative x, all divided by 2. We're going to see that the sine and cosine actually have similar, well, the sine and the cosine, I don't know if we will see it today. The sine and the cosine can actually be defined in a very similar way, but we have to use the imaginary unit I in order to do it. And we'll see that the sines and the cosines and the hyperbolic sines and the hyperbolic cosines are related to each other via the complex and imaginary numbers. Incidentally, the 4 other hyperbolic trig functions we won't talk about today, but defined in a perfectly natural way. The hyperbolic tangent is the hyperbolic sine over the hyperbolic cosine, and so on. So like if I go to Desmos and I look at the hyperbolic sine, let's try that again. It looks, I guess, vaguely like a cubic polynomial. It grows so quickly that it might look as if it's growing to infinity, as if it has some kind of a vertical asymptote. It does not have, let me make this less awful to look at by letting x be more limited. It does not have any kind of vertical asymptote. This very swift growth is coming from the fact that it's defined or can be shown to be equivalent to an exponential. I mean, you see this exponential here, and as x gets big, e to the x goes very quickly to 0. So we're seeing something that looks a lot like e to the x divided by 2. And because e to the x grows so quickly, this hyperbolic sine also grows quickly. I mean, there you go for comparison. On this scale of magnification, they look identical up here. And then the hyperbolic cosine same sort of thing. The hyperbolic cosine sort of looks like an even polynomial, like x squared, but it grows vastly, incalculably faster than x squared. And again, this very rapid growth, you see x is only at 6, but this is at about 250. This comes from the fact that the hyperbolic cosine can be defined in terms of e to the x, and e to the x grows like that. I keep struggling over the word define because I defined the hyperbolic sine and the hyperbolic cosine using geometry. So it's a little awkward to keep talking about definitions, but a lot of textbooks will skip the geometry and just define the hyperbolic sine and the hyperbolic cosine in terms of the exponential. And, here's the hyperbolic cosine. I'm claiming that this is e to the x plus e to the negative x, all divided by 2. And we see that we do get the same graph. Desmos, I have no idea what Desmos thinks it's finding down there. So the hyperbolic sine and the hyperbolic cosine sort of sometimes seem like they should be similar to the sine and the cosine, and sometimes they seem like they should be completely different. I mean, they're defined in a kind of similar way, but they're also defined in terms of e to the x. They're these extremely quickly growing functions compared to, if I put the cosine on the board, it's just stuck down here between -1 and 1. So obviously there are similarities and there are differences. As an example of something that's both a similarity and a difference. The standard sine and cosine that we're all used to satisfy the Pythagorean identity. The cosine squared plus the sine squared equals 1. So the difference between the unit circle and the hyperbola is that the unit circle is addition. So all we did in this definition was take that addition, turn it into subtraction. That's reflected perfectly here. The hyperbolic cosine squared minus the hyperbolic sine squared equals 1. Similarly, the derivatives are similar but not quite the same. I don't need you to memorize a bunch of derivatives. I just want you to have seen this so that if you take differential equations with me, you're not blindsided when this stuff shows up. but the derivative of the hyperbolic sine is exactly what you might expect it to be. And once again, the difference between the derivative of the hyperbolic cosine, you might expect it to be the negative hyperbolic sine, but just like over here, it's off by a negative sign. The derivative of the hyperbolic cosine is the positive hyperbolic sine. So we keep seeing these properties that are similar to the standard sine and cosine, but not quite the same. And the sine and the cosine and the hyperbolic sine and the hyperbolic cosine have a very famous relationship. I mean, to the extent that you want to call any of this famous, that requires a bit of complex analysis to tease out. So here's a formula. It doesn't involve the sines or the cosines or anything else. E to the ix is the cosine of x plus I times the sine of x. This I do feel sort of justified in calling famous. It's Euler's formula, Euler's identity. The second word changes, but it's definitely Euler's. Often considered maybe the greatest mathematician to ever live. These things are always kind of fuzzy, but this is something we're going to prove later in the semester. This is turns out to be a very nice application of infinite addition, of infinite sums and series. So we're actually going to prove it as a calculus exercise, but for now, we'll just state it and accept it. And I've said that when I put these on the board, I said, well, we have similar statements for the sine and the cosine, but we need the imaginary unit. Does everybody here, I guess I should ask this explicitly, know what I is? What I'm writing on the board. I is informally the square root of -1. And it's sort of misnamed the imaginary unit, even though it shows up in like radio waves and all sorts of real world and not imaginary applications. So if we just replace x with negative x, we get this formula. This might not be super immediately obvious. You might think I must be missing negative signs, but we're replacing x with negative x, and we're using the fact that the cosine is even, it's symmetric around the y-axis, and the sine is odd. It's symmetric around the origin. So when we replaced x with negative x, the cosine doesn't change. The sign gets a negative sign in front of it. And we can use this to get the sine and the cosine in terms of the exponential, in terms of the convex exponential. And in particular, if we take both of these things and we add them together, e to the ix plus e to the negative ix is 2 times the cosine of x. The positive sign and the negative sign cancel with addition, and we divide both sides by this 2. And we get that the cosine of x is e to the ix plus e to the negative ix, all divided by 2. And this is precisely the hyperbolic cosine, except that now we've got some imaginary units thrown in. It's maybe a slight irony, the sine and the cosine, which we use every day in these classes, and which maybe seem like they ought to be simpler, require the imaginary units, whereas the hyperbolic sines and cosines, which seem exotic, can just be defined so that a college algebra class could understand them. But let's see. If instead of addition, we did some subtraction, e to the ix minus e to the negative ix equals the cosine minus the cosine goes away. Here we have minus a negative. And we divide by 2I this time. We get the sine of x is e to the ix minus e to the negative ix, all divided by 2I. And in spite of using the imaginary units, these definitions of the cosine and the sine, I say definitions, I don't quite know what other word to use, these alternate definitions, if you prefer, can be very useful in very concrete settings. Like probably nobody in this room really remembers all of the identities that we were at one point required to learn in a trig class. But a lot of identities become very easy to prove if you use this definition of the cosine and the sine, just because e's are easy to work with. We can multiply them, we can distribute them, we can do whatever with them, whereas the sine and the cosine are defined in terms of the unit circle, and it's hard to know what to do. You know, not to dwell on this too much. But if we want to multiply the cosine of x and the cosine of y, then if we just have the unit circle, it's not at all clear what this ought to be. Here, that we can distribute. We wind up with 4 terms in the top. E to the ix times e to the ix, e to the ix times negative e to the negative ix, and so on. And when you have the same base, that multiplication turns into addition. So if we just take that 2 out, so when I just put this on the board in silence, it probably looks intimidating, but x plus my notes are messed up for one thing. There we go. Just doing the cosine times the sine there. So I mean, this e to the I x plus y is just this term times that term. This e to the negative I x plus y is just this term times that term. So we're just doing the foiling, we're doing all 4 multiplication, and we're grouping them a little. And then this is the cosine of x plus y. You see this x plus y here. This is just the definition of the cosine with x replaced with x plus y. And this is the sine of x plus y. No, it isn't. I keep making these weird little errors, even though I've claimed this is easy. Lesson to us all. This is the cosine of x minus y. Again, you see we have an x minus y and an x minus y. This is the definition of the cosine, except instead of x, we have x minus y. So arguments like that, which obviously I repeatedly botched, but at least I sort of had a method of approaching this. I have no idea what I'd do if you told me that I was supposed to prove this using the unit circle. Whereas with these exponentials, we can just do the multiplication and see what happens. Relating the sine and the cosine and the hyperbolic sine and the hyperbolic cosine further. Let's see. So I've put Euler's formula on the board. And I've made the observation that that gives you this. And I've given you a definition of the so let me see. So the hyperbolic cosine of Ix is e to the Ix plus e to the negative Ix over 2. I'm not doing anything clever here. I'm going back here, and I'm saying, well, this is the definition of the hyperbolic cosine. So like the cosh of 5 would be e to the 5 plus e to the negative 5 over 2. I'm just plugging Ix into this the exact same way you'd plug any other number or expression into this. But this is defined in terms of e to the x and e to the negative Ix. And those in turn are defined in terms of the cosine and the sine. So this is the cosine of x plus I times the sine of x plus the cosine of x minus I times the sine of x, all divided by 2. The signs cancel. We have a negative and a positive 1. Again, seems to be my day for just writing stuff at random. That's the cosine of x. So there's this relationship between the cosh and the cos, the hyperbolic cosine and the regular cosine, which is that they're off by an I. If we take a number and we make it purely imaginary, then the cosine turns into the hyperbolic cosine, essentially. And there's something similar for the hyperbolic sine as well. And the hyperbolic sine and the hyperbolic cosine allow you to compute the sine and the cosine of imaginary numbers. Like what's the cosine of the imaginary unit? Well, according to the formula on the previous board, written in a different order, the cosine of a value is the hyperbolic cosine of I times that value. So the cosine of the imaginary unit is the hyperbolic cosine of I times I. So one of these i's is coming from here. This x is an I. The other I is coming from the formula, right? I squared is -1. The hyperbolic cosine of -1 is 1.5430. So we can take the sine and the cosine of complex and imaginary numbers, or at least of purely imaginary numbers, using the hyperbolic sine and the hyperbolic cosine. Again, this is not something you could do with the standard definition of the sine and the cosine in terms of the unit circle. And there are other methods you could use. Again, we'll talk about those. They involve infinite additions, but this is probably the most straightforward. And the other method, because it involves an infinite sum, you could not just go to Desmos and plug it in and get it. So I think, I don't think, well, in fact, I know that Chadron state does not have like a dedicated complex analysis class that is normal for small liberal arts institutions. The one I went to also didn't. But it's some really interesting stuff, or at least I find it really interesting. So like, this statement here means that on the complex plane, e to the ix is a periodic function. We're used to e to the x just growing very quickly without bound, but because it's defined in terms of the cosine, which has period 2 pi, and the sine, which also has period 2 pi, the imaginary exponential e to the ix is periodic with period 2 pi. So on the imaginary axis, it does not go up to infinity, it bounces around. So stuff like that, we can at least get a taste of today. And I don't know if I really have homework for this section. I mean, I can take a look at the textbook, but I think it's mostly pretty banal, like finding derivatives of hyperbolic trig functions. Mostly I just want you to see this because it is important material and it's sort of a gap in the standard undergraduate math curriculum. With that, I guess I will see you Monday of next week. Have a great weekend.